Okay, please turn to page 9 of your notes if you haven't already. So the first thing we're going to talk about is Lagrangian versus Eulerian analysis. And Lagrangian analysis is what you did in physics. So for example, if you're tracking a baseball as it flies through the air, that's Lagrangian analysis. Eulerian analysis, on the other hand, is control volume analysis, which you've seen before. So if we just fill out these examples, so indicate which uses Lagrangian versus Eulerian analysis. Projectile motion in physics class, well, Lagrangian. A turbine in thermo, Lagrangian. Most of fluid mechanics, Eulerian, because we're going to be following, it doesn't make sense to follow a fluid particle as it goes through space. There's just too many of them interacting with each other. So it's going to be Eulerian analysis, control volume analysis, right? So what happens is things get a little bit more complicated. And let's start talking about velocity vectors in particular. So our velocity vectors, we're going to use those a lot in fluids. And they are now in control volume analysis not just going to be a function of time like they were in physics. So if you had a baseball flying through the air, well, its position, its x position, its y position, its z position was a function of time. Its velocity and accelerations were also a function of time. But time was your only independent variable. Now, with control volume analysis, we're going to look at the velocity vector and how it changes in space as well as time. So velocity vectors are going to be a function of x, y, z within your control volume, or position in your control volume, as well as time if it's unsteady. So what I mean by that is, let's say that we're at time equals 0. And again, at a different time, this will look differently if it is unsteady. So let's go ahead and put a coordinate system inside our control volume, and we'll just do 2 dimensions for now. If you look at this particular position, position 1, it's got an x1 and a y1, it's going to have a velocity vector at that point. So velocity there will be a function of x1, y1, z1, and we'll call this t1. Okay. But if we look over here at a different x and y position, we got a different velocity vector maybe. x2, y2, z2, it's still time 1, this case. All right, so basically our velocity vector is not just that baseball, it's going to encompass a whole region in space. Okay, that makes it a little bit more complicated, but it also holds a whole lot more information. So the other thing about velocity vectors, besides they're just changing around in space, is since they are vectors, they're going to have 3 components. You got your x, y, and z, or your I, j, k components of the velocity vector. And what we're going to do to simplify things a little bit is to call the x direction component u, the y direction component v, little v, and the z direction component is little w. So that it's just going to give us a little bit of nomenclature. Now this is going to be very important that you remember this. So because if we say that u is blah blah blah, you got to remember, oh, that's my x direction of my velocity component, velocity vector. So if you take that u, v, and w, take your velocity vector, break it into its 3 components, what that means is your v is equal to u times I plus little v times j plus little w. Oh, shouldn't have put a vector on that. Little v times j plus little w times k. So that's your velocity vector. Now u, which would be just the x component of this v, u changes from spot 1 to spot 2, right? So u is a function of x, y, z, and t, and so is little v a function of x, y, z, and t, and so is w a function of x, y, z, and t. All right, so 4 independent variables for each of those. By the way, the book uses a bold V to indicate the vector V, just so you know. All right, a lot of times we have the velocity just going in one direction only, so we'll just call it u. And so we won't have to break it into its three components, we'll just call it u if it's only going in one direction. You have to remember though, even though it's going in one direction, u is just still a function of all these things possibly. And so in fact what we'll do is draw what are called velocity profiles, which shows you that velocity vector and how it's changing over your control volume. So for instance, if we have a pipe, it's just a cutout of a pipe. If we draw a line here, we say at this position, x position, our velocity is going to be changing across that pipe. It's actually highest in the middle, and it turns out to be 0 at the walls. You're going to get something like this. All right, and what we do is just draw little arrows indicating our velocity and how it's changing across that y. In this case, it's just changing with the r direction, the radial direction. So that's a velocity profile. We use those a lot. And that's what I got for this little video, so please stop and take quiz problem 6 now, and I'll see you back for the finishing video for this lecture.